wish to thank the organizers, especially Dr. Eduardo Arz, for the invitation and giving me the opportunity to share part of our research with you. As many of you know, I recently joined the IBioBA after many years in the United States, so the results that I'm going to present now basically where the research was done in the United States. My group there, the people whom I wish to thank are basically co-authors in the papers that I'm going to show, and I also wish to thank there the funding from mainly NIH and the Welch Foundation. The goals of this presentation is I want to give a brief overview of how biomolecular simulation can aid structural biology and drug discovery. Yesterday we had two impressive talks from Daria Strain and Helmut Grubmüller on the area of simulation. So this is a follow-up showing simulations in a slightly different area. I will try not to be too technical. The technical details are better laid out in the papers. I just want to give more conceptual idea and of our research and things that are usually not described in the papers. I also want to stress, for example, the approximations involved, the range of validity. I'm going to present 3 or 4 case studies, I mean time dependent on time, on computer-aided drug discovery, protein modeling, calculation of binding free energy, and if time allows, a little bit of charge transfer. And then I also want to give a sense from my talk of what cannot be done. Simulations are really help. It's a good help to the experimentalist. There are many things that can be done. Not everything can be done. So, what are the advantages of computational simulation? So, well, in general, it allows to predict properties that might be difficult to determine experimentally. So, for example, modeling transmembrane proteins such as GPCRs, which, as Professor Huber remarked, are quite difficult to crystallize. Or we can study, for example, protein dynamics, which is hidden, for example, in an X-ray structure. In general, simulation is flexible to change the system conditions. So, for example, it might be useful to study or to determine the structure of a protein complex with a non-native ligand. Simulation is usually fast, or could be fast and cheap. So, for example, it could be used in computer-aided drug discovery to help to save time and cost, especially in the early stages of the drug discovery process. And it bridges basically the microscopic and the microscopic and the macroscopic world. For example, doing molecular dynamics, it's a microscopic, I mean, it tries to reproduce the microscopic behavior, and from there we can get macroscopic observables. I want to remark also in line, which was presented yesterday, that it's a complement and not a substitute to experiments. So everything that is basically simulated, or many things that are simulated, or many of the properties that are simulated should be somehow experimentally validated. Main components of biomolecular simulation, I will try to go, I will try to go fast on this. So we need the structure of a system, so we need to know how the system is basically composed, the identity, for example, of the atoms, and bold X, I mean the position of those atoms. Then we have to decide how we are going to represent the system. If we are going to use nuclei and electrons, if we are going to use just atoms, if we are going to use potential energy maps or coarse grain, we have to decide that. Depending on that, on those choices, we have to define the level of theory. For example, if we are going to do quantum mechanics, we have to choose, for example, it's DFT, it's going to be ab initio, semi-empirical, and in DFT, well, we have to choose the functional. Then we need a potential energy function that basically is what's needed to simulate the system, and then an algorithm to explore the potential energy surface. Basically, broadly speaking, the system can be described in terms of quantum mechanics, which is accurate but computationally more expensive. In this case, usually the nuclei are considered like point charges, and the electrons are described through a wave function. The wave function is obtained by the solution of the Schrödinger equation. Or classical mechanics, where the atoms, I mean, the nucleus and the electrons are condensed in a point particle with a mass, a charge. And the interaction is governed by the laws of classical mechanics. For example, in this case, the bond, each bond is represented by a harmonic oscillator, as is described in the third term of the second equation. And then there is also a term for bond angle, for planar angles, and a term for torsions. This is a very general expression. You can add some other terms, but this is the most general expression. Well, at some point, we have to decide which is the approach that we are going to take. And well, the approach depends, of course, on the property of interest, on the required accuracy, and the computational power. So we have to make a choice on this. It has to be a smart choice. So I'm going to try to present 4 case studies. I'm going to briefly describe them in case I don't have the time to present all. The first is a computer-aided drug lead discovery project. So here, what we do is a fast structure-based virtual screening of thousands of compounds to determine those with a higher chance to bind to the receptor. Then that subset is bioevaluated to check if it's going to bind or not. In this case, the ligand is represented by force field, I mean, classical mechanics, but the receptor is represented by energy maps. And the reason for this is that it's much faster. The second case study is a ligand-protein interaction guiding protein modeling. So here we try to, in silico, characterize the binding site conformation of a protein through a simulation of the ligand in the binding site. Here, the ligand and the protein are both represented by a force field. The third is studying biomolecular interaction with quantum mechanics. So here we try to do an in silico calculation of binding free energy in a peptide protein system using a full QM quantum mechanics representation. So both the ligand and the protein are QM. So this is not QM-MM, one part quantum mechanically described, the other molecular mechanically. This is full QM. And the fourth is studying protein-water charge transfer, where again protein and the solvent molecules are represented in a quantum mechanically fashion. So a couple of slides on conceptual introduction. The concept of docking, as Dario Strin said, yes, it's very simple. It's just the prediction of the ligand conformation and orientation, that is the pose within the binding site. So on the left you have a protein with a pocket with a binding site, and through ligand docking, a ligand is positioned and oriented in that binding site. So the idea is, if we are going, if we want to perform a screening and to find binders for a protein, so you have a target, you have a chemical library, you can do high throughput screening. So you do that experimentally, you might find some hits or leads. The other possibility is to do a sort of virtual high throughput screening or a high throughput docking. So try to do that in silico, in the computer. So try getting molecules from a chemical library and trying to dock each molecule one by one, and then give a score to each molecule. And the top scoring compounds, the top scoring molecules are bioevaluated. So we just bioevaluate a subset of the total library. So this is a rational selection. I'm not selecting all or selecting at random. I'm just selecting those which have a better chance of binding to the receptor. So if we want to describe the process in a matricial way, I'm a physicist, so I'm very keen to this type of representation. If we go horizontally, I mean, we have a receptor, we have a molecule, and we determine for each of the molecules the complex. And each complex is then scored, is given the likelihood that that molecule will bind. Just a brief comment, that score ideally would be the binding free energy, but that's ideal. Since we cannot do that, we have to, usually the scoring functions have 5, 6, 10 parameters which are somehow fitted before the docking, and that score is used. It's not the ideal solution, it's the best solution we can give right now. On the right of the slide, that's the typical outcome of a virtual screening. That's a virtual screen on the androgen receptor, 350 kg molecules. There the molecules are sorted, I mean, characterized by mass, and the score, the more negative, the higher the chance of binding. Well, the first case study is a virtual screen on the epidermal growth factor receptor. It's a protein involved in cancer. There are tons of known inhibitors. Some are picomolar. Why we did this? Well, we did this because in 2003, the first crystal structure appeared, and we wanted to see if we could find something new, something novel. So this was the first the virtual screening on the crystal structure. This is the basic visual screening high throughput docking flowchart. On your left, well, you know you need the structure of the protein. When I mean with the structure, I mean the experimental structure or a model. On the right, you need a chemical library, something to screen. And then the process is, with those, you dock, you score, and after that, you come to the post-screening stage where, well, you sort by score, you perform chemical clustering of the molecules, visual inspection, and we selected 50 compounds, which were tested by my collaborator, Javi Piedrafita, in San Diego. So we came, we found quite a few that showed anti-proliferative effects. That's the bottom, the right bottom slide. But not all of them were appeared to be EGFR inhibitors. Probably they were inhibiting or targeting some other protein in the pathway. But we found this 39, this compound that had an IC50 of about 10 micromolar. The second slide showed it was a true ATP competitive inhibitor. And the picture shows the compound 39 superimposed to IRISA, which was the native ligand in the crystal structure. So it was an interesting work. We honestly expected to find something perhaps with a better activity, but well, just to have a hit with 10 micromolar is not bad. So this approach, this high throughput docking, well, it's good or bad. It provides a rational approach to drug discovery. So the goal is to enrich the hit list with potential binders and to find some novel chemotypes. It's not to find everything. And sometimes, for example, we do a virtual screening and the experimentalist finds nothing. And he says, well, but I found nothing. Well, the problem is that if you take a chemical library to find something, the potential ligand has to be in the chemical library. So we discover, we are not creating. This is not a de novo design, which can be done. But the de novo design has a problem that you can make beautiful compounds that actually might bind, but somebody has to synthesize them, and that's a problem, or might be the problem. This is fast, it's a low cost, it provides a tentative bound structure of the complex, which is very good if you're going to continue with lead optimization. Pitfalls, well, of course, false positives, false negatives, poor binding energy prediction. Poor binding energy prediction. Don't believe papers where compounds are sorted by binding free energy given by autodock or dock or any docking compound. That energy, this fast docking cannot accurately predict binding free energy. Can give an idea which molecule is going to be on average statistically better than others. Well, of this project, the most interesting part is perhaps the motivation. I was working in a biotech company. We were approached by Schering-Plough, and they wanted to do drug discovery on the melanin concentrating hormone 1, which is involved in obesity. They had already several ligands, good ligands, nanomolar ligands. They were published, I think, in a JMed Chem from Clark in 2000 something, but they wanted something novel, and this was a challenge. Was indeed a challenge. MCH, it's a GPCR, so we know that it has a structure, a fold of 7 helices arranged in a certain order, but there's no crystal structure. By then, this was 2004, 2005. There was just one crystal structure of a GPCR, which was bovine rhodopsin, and there is also very low sequence similarity among GPCRs, but there is high structural similarity. You know that all GPCRs share a common fold. So the goal for me was to develop a general methodology to model binding sites aimed to be used in computer-aided drug discovery. So the quality that I was asking to the model was to be good enough for structure-based virtual screening, to be used to predict ligand-target interactions, and to aid in the design of mutagenesis experiments. The goal was not to model with high accuracy regions far from the binding site. So that has to be kept in mind. The usual homology modeling method works like this. You have a protein you want to model, you try to find a similar homolog protein which has a structure, and then you do an alignment and you try to get a model, which of course is unrefined. So my added value to this was, if we know some ligands of that protein, why don't we use that information to shape the binding site? So that's what I did with MCH. We got some ligands, we generate an ensemble of binding sites, we filter these, we cluster them, and we use those binding sites for a structure-based virtual screening, for a real, and we selected 150 compounds, 129 were purchased, 6 were found with less than 20 micromolar, which was an interesting result, provided that This included the model of the protein and the visual screening and bioevaluation. So it was a pretty rounded paper. Then later on, 2 years ago, we continued doing a formal validation of this methodology, because since 2009, several GPCR crystal structures appeared. So we used that to benchmark and test our method. This is, for example, two slides showing the modeling of beta-2 adrenergic receptor from bovine rhodopsin and from A2A adenosine receptor from beta-2. It's not perfect, but it's a huge advance and a huge improvement compared to just plain homology modeling. When I mean plain, is unrefined. So brief conclusions of this part. So high-throughput ligand docking is a legitimate tool for computer-aided drug discovery. The models using the ligand to shape the binding site are indeed of better quality than just plain homology models, and those models were really useful in visual screening. Let me now switch a little bit to another project, which is a bit different. And there is a paper published in 2005 from Wu and Benoit Roux, calculating the binding free energy of a phosphotetrapeptide to the SH2 domain of human LCK. So as you see, the experimental value and the calculated value are quite different. We didn't know what was happening, so we decided, since the phosphopeptide is strongly charged, that why don't we use quantum mechanical methods to describe this system and calculate the binding free energy. So the advantages of using quantum mechanics is that, well, it accounts for polarizability and charge transfer in a natural way, systematically improvable. It offers, when you deal with small molecules, it offers a greater freedom to deal with non-standard molecules compared to a force field. Our level of choice was semi-empirical methods, because that is what we can afford. Well, this is a slide about the beauties of semi-empirical methods, which are quite better than what people would expect. In this, well, this is described in the JCC paper. I will just focus on the framed equation. That's something that basically can be derived, and that's the equation that it's usually found in molecular mechanics, Poisson-Boltzmann surface area methods, the MMPBSA or MMGBSA. Here, the binding free energy is calculated as it's an endpoint method. So you calculate the properties for the complex and the property for the protein and ligand in isolation. So this is, well, basically is the difference of the, well, mean value in those states of the energy in vacuum, its solvation term, and the entropy term is split in a rigid body contribution and an internal entropy contribution. The hypothesis here is